Comparison of Martian hematite spherules and Earth's concretion analogues. It has been suggested by various scientists that the Martian hematite spherules are concretions. Because concretions are formed by water on Earth, this carries the significant scientific implication of proof of water in Martian history. We will first examine the properties of Earth's concretions to see if they are suitable for classifying them as terrestrial analogues of Martian spherules. A concretion is a compacted mineral body that is embedded in a host rock, which has a different chemical composition. Terrestrial concretions are formed from liquid phase by precipitation, nucleation, and growth processes. The concretions can grow in size and are found in various sizes and shapes. They are rarely perfect spheres and have no size limitation. Examples of terrestrial concretions: Jurassic Navajo sandstone, southern Utah, which have been cut to show their internal structure, are displayed in. The concretions are usually round objects with heterogeneous internal structure and are rarely perfect spheres. They are not limited in size and can grow to a diameter of several centimeters and even meters. Also shows a steel ball with a diameter of 6.4 millimeters. The blueberries on Mars are all less than 6.4 millimeters in diameter and have similar physical properties to the steel ball. Earth's concretion analog samples from the Jurassic Navajo sandstone, southern Utah, courtesy William Mahaney. A 6.4 mm diameter steel ball is also shown for size reference. Next, we look at the chemical composition of the concretions found on Earth. Raman spectroscopy is considered as a fingerprint technology for chemical identification. Raman spectra represent the vibrational modes of a molecule, and all different chemicals have unique Raman spectra. For example, no two chemicals have the same Raman spectrum. Hence, Raman spectra can identify a chemical with 100% confidence level. Presently available commercial Microraman systems are capable of identifying small mineral grains in the nanogram range. Microraman spectroscopy with 785 nanometers laser excitation has been used to identify the chemical compositions of Earth's concretions. Raman spectra were measured at multiple locations on all the samples. Shows representative Raman spectra of hematite, rose quartz, and goethite with both brown and black grains of Earth's concretions. The Raman spectra of the brown grains of concretions, which are located inside of concretions, are same as the Raman spectrum of quartz. This confirms that the interior composition of Earth's concretions is quartz with grain size of the order of 150 microns. The outer darker layers of the concretions also show the quartz Raman band along with Raman peaks of goethite. This suggests that the dark layers are made of quartz coated with a thin layer of goethite. This chemical analysis of Earth's concretions suggests that they are not hematite, which is consistent with reference. The Raman spectra of concretions shown and confirm that the interior of the concretion is mainly quartz. The outer dark grains are made of quartz, which are coated with goethite. In the formation of concretions, water-containing dissolved minerals cement around the grains of the host matrix, which is why grains of host matrix are always included in the Earth's concretions. In fact, none of the concretions on Earth are made of pure hematite, they can be hematite-coated quartz or calcite. The concretion mechanism cannot remove the grains of the host matrix, quartz, calcite, etc., and replace them with pure hematite mineral. It may be possible to form pure hematite crystals from an aqueous solution, but it will have the shape of a crystal and not a perfect sphere. A recent attempt to form spherules by freezing an aqueous hematite nanoparticle suspension failed in a laboratory setting. The concretion model does not explain the following: I. Why are the Martian hematite spherules limited in size? 2. Why are the spherules pure hematite? And 3. Why are grains of the host soil missing from the interior of the spherules? The formation of concretion from aqueous media also leads to another interesting fact: concretions are formed deeper in the soil. This is because during the dry season, the level of groundwater goes down. This increases the concentration of dissolved chemicals in the subsurface soil, which favors the formation of concretions in deeper soil. For Earth's concretions, a relatively larger number are observed in the deeper soil than the top surface layer. In contrast, the Martian blueberries are mostly concentrated within 1 centimeter of the top surface. No blueberries were observed in the deeper soil when trenches were excavated on Mars as shown in. In addition, Earth's concretions are not as shiny as some of the Martian blueberries. This is because on Earth erosion plays a critical role in the formation of concretions. Concretions are formed inside the host matrix and are released from the host matrix by eroding away the surrounding material. The erosion of surrounding material takes several thousand years. Therefore, it is easy to see signs of erosion, pitting, and flow patterns due to the presence of aqueous media on Earth's concretions, which appear as dull metallic-looking objects. The erosion process plays a critical role in the formation of concretions and dictates that the Earth's concretions are very old. Shows an image, Sol 251, of a large 1-meter-long rock, Wapme, found on the Endurance crater, showing hundreds of blueberries on its surface. The NASA science team suggested that the blueberries in the region are embedded in the rocks and eroding from them. One of the problems with this conclusion is that all the blueberries observed on the rock are fully exposed spherules and no blueberry is seen emerging from the rock. It is expected that the erosion process would reveal some partially exposed blueberries on the rock if they are concretions. In addition, rock erosion produces soil that has a similar reddish color as the rock and would be mixed in with the bluish-looking soil. Lastly, the distribution of blueberries in the region and around the rock is consistent with a hypothesis that they fell from above. Region A, which is near the slope of the rock, shows a high concentration of blueberries as compared to Region B, which is away from the rock. Also, in Region C, in the shadow of the rock, there are no spherules, which contradicts the concretion mechanism. Another interesting observation is that spherules are heavy and therefore not easily transported by dust devil events. Otherwise, there would be no spherules on the slopes of the rock and Region C would be filled with spherules. The observation of spherules on Wapme rock suggests that blueberries fell from the top and are not eroding out of the rocks. The hypothesis of deposition of blueberries from the top is also consistent with the observation that the entire blueberry inventory is within 1 cm of the top surface layer. Image showing hundreds of fully exposed blueberries on Wapme rock and nearby area. No blueberries are observed in Region C, Sol 251. Image courtesy of NASA/JPL.